Hello everyone, my name is Srishti IJCNN. I am a student at Indian Institute of Technology, Roorkee. Today I am going to present my work titled Unveiling Robustness of Spiking Neural Networks Against Data Poisoning Attacks. My paper ID is 1570993254. This work I have co-authored with Anshul Pundir, Balasubramanian Raman and Sanjeev Kumar. This work has been accepted at International Joint Conference on Neural Networks 2024, which is under the flagship of IEEE World Congress on Computational Intelligence. So this will be the outline of this presentation. First, I'll give a brief introduction and motivation for this work. Then I'll introduce a brief literature review regarding this work. I'll discuss some of the preliminaries needed for in this work, and I then followed by my contributions, methodology, data sets and experimental setup, results, and finally I'll conclude this presentation. So first of all, introduction and motivation. So as we all know, deep learning models have shown exceptional performance in many challenging and crucial tasks. Some of the critical areas where deep learning is performing exceptionally well are healthcare, imaging and vision, image classification, hyperspectral imaging, and many more. The computational requirements for training deep learning models has shown a significant growth by a factor of 300,000 from 2012 to 2018, shown by a research by a paper titled Green AI by Roy Schwartz. Next, also in Dhar et al. In their works highlighted the impact of artificial intelligence on climate change and have emphasized on using sustainable AI. Recently, researchers have shown active interest in a new type of neural networks, which are called spiking neural networks. They are considered to be more energy efficient compared to their counterparts, such as convolution neural networks, recurrent neural networks, artificial neural networks. SNNs are sometimes also referred as third generation neural networks. So basically, in SNNs, they process information when a spike train is received and therefore gain efficiency by exploiting event based data-driven updates. SNNs have shown application into various domains, which are image classification, object detection, EEGs, pattern recognition, etc. To achieve better performance in deep learning models, we need a huge amount of data for training our models. Handling such vast data sets make them vulnerable to adversarial attacks such as backdoor attacks, Trojan attacks, linkage attacks, model inversion attacks. One such particularly dangerous and straightforward attack is data poisoning attack, which can occur during data collection, data processing, and on further stages also. And so we focused on in this work, we are focused on data poisoning attack, which mainly works on the principle of poisoning the data in order to misclassify the prediction or manipulating the predictions generated. Now I'll give you very brief literature review. So in Yunjuan et al. In their work, used AlexNet and a two-layer CNN model to test stochastic gradient descent robustness against clean label attacks and label flipping attacks. Fiery et al. Used six different type of machine learning models and used random label flipping and distance-based label flipping to study the behavior of different machine learning models under label flipping attacks. Well Tolpigin et al. Studied the effect of label flipping attack by adding the malicious participant in federated learning models and observed the accuracy drop by 6%. So these were some of the very brief literature review. There are more. Please refer to our paper for more literature for more such works. So these studies shows that a wide range of research on the effects of data poisoning attacks and mainly focus on machine learning and deep learning models only. So basically, SNNs are very underexplored for their potential against such attacks. In this paper, we provide a detailed analysis of three different kinds of data poisoning attacks on SNNs using three different data sets. Preliminaries, we are going to discuss. There are many more models, SNN-based models, such as Hodgkin-Huxley models, leaky integrated fire model, HKVH model, and many more. In this work, we have used leaky integrated fire model. It is one of the most widely used models to analyze the behavior of SNNs. The neuron is considered leaky since the membrane potential decays with the membrane time constant tau nt. So a life model can be described as we have shown in equation 1, and we have also shown the notation of each and every term we have used. Next, in this figure 1, you can see the working of a live neuron model, in which first we convert the input into spikes, and then they pass through a live model, which will further pass through further layers when they exceed a predefined threshold value. Next, preliminaries is spatial learning through time model. It was proposed by Meng et al. The goal of proposing this model was to reduce the time and computation cost compared to vanilla backpropagation to time model. They use triangle function as surrogate gradient descent since as SNNs are binary like event based models, so it is not possible to differentiate them for backpropagation. So we use surrogate gradient descent for LIF for SNN. Sorry. So in this case, we have used triangle function. In SLTT, triangle function was used. So membrane potential is updated using equation 3. In SLTT methods, the authors found that temporal components contribute very little to calculation gradients, so they used only spatial gradient and showed a significant reduction in memory and time consumption. Next, I'm going to discuss the contributions. So first, our first contribution is to that to the best of our knowledge, we are the first to provide in-depth analysis of effect of different data poisoning attacks on SNNs. We proposed different data poisoning attacks on different data set and carefully examined their performance on large-scale spiking models, spiking regional 18 and spiking VGG level. We develop a novel performance metric to evaluate the robustness of model against data adverse serial attack. Finally, we propose a lightweight yet robust synapse-driven spiking neural networks that significantly surpasses the large-scale SNNs. Methodology in this section, I am going to discuss how I have implemented the three different how we have implemented the three different type of attacks along with the model that we have proposed and the metric that we have proposed. So first of all, I'm going to discuss the problem definition. So first, we can consider SNN model CM and training dataset D. The collection of data samples is denoted by X and the corresponding labels as Y. So we denote DC as the clean data where the labels and the images are untouched, and DP as the poison data where we have kept the images same but we have changed the label. So the training data set then can be defined as the combination of clean and poison data set. So consider that suppose we represent CS as the source class and CD as the target class. The adversary's objective is to change the label Y to new label Y star to create a poison data set. Also, the adversary determines the percentage of data to be poison, denoted as P. Here we assume that adversary has complete knowledge of the data set and can change the data as per he wishes. So in attack 1, we are using fixed target flipping attack. The adversary select a source class and a target class, then proceed to invert the labels of the source class with predetermined target class. For example, if our source class represents trouser and and our target class represents bag, after applying attack 1, P% of trousers will be relabeled as bags. This is the algorithm that we have used for fixed target flipping attack. Next, in attack 2, we have used random target flipping attack. In this attack, the source and target classes both are randomly selected. The whole process is entirely stochastic. The adversary can only decide the percentage of the data to be poisoned, and the source and target class are chosen randomly, and the labels are also flipped randomly. So this is the algorithm that we have used in random target flipping attack. The third attack is source target blending attack. It is quite different from the previous two attack. In this we have used data augmentation as an attack. In this process, we have blended the source image with the target image in the ratio with 50%. Like we have kept the ratio as 50%. So also please note that we have kept the labels of the source image same. So yeah. This is the source target algorithm for source target blending attack. Next, I'm going to discuss the model that we have proposed. So we have designed this using spiking jelly framework. This is the architecture of the model. So in this model, we have used to recall the memory state, we used the synapse filter in the network architecture, which helped us in improving our performance in the classification. We further set up a feedback connection block for process features that help refine the features for error correction and class prediction rate. So yeah, this is the architecture that we have used. In this figure, we can see the spike features generated in the proposed model during the first timestamp and final timestamp. So next, I'm going to discuss the metric that that we have proposed. So in this, during the experimentation part, we observed a very strange behavior in spiking resonate 18. That is, it was first showing an increase in the performance and then it was decreasing to show a fair decrement in the performance. We proposed attack diversion score. It considers all the accuracy attained by the model, that is before applying poison attack, during the subsequent extent of the attack, and then provides some maximum change in the accuracy due to data poisoning. Next, we are going to the data sets we have used. We have used three different data sets, MNIST, FMNIST, and ISEC 2019. So MNIST and FMNIST are grayscale images which consist of 10 different classes, whereas ISEC is a binary data set which consists of melanoma and non-melanoma images. Experimental setup, we have used Ubuntu 22.04 operating system and models were deployed using PyTorch. We have used Spiking Jelly to implement SNN. We have used NVIDIA V100 GPU with 16 GB of graphical memory. We have used mean squared error as a loss function. In results section, we have in this section we have this table 1 where we have shown the comparative analysis of all the three models on all the three data sets during attack 1. Here we can we can see that the ADS score is better for our model in the case of a skin data set, whereas in other two data sets it's showing comparative performance to spiking resonatine and spiking BGG11. In attack 2, we can see that our ADS score is better for in all the three data sets for our proposed model. In attack 3, we can see that our ADS score is better for skin FNIS dataset for the proposed model, whereas for FMNIS, spiking BGG11 is more robust, although our model is also showing comparative performance. In this figure, we have shown bar plot to give a comparison of proposed model with other spiking models during different data poisoning attack for skin dataset. In figure 5, we have given a comparison of performance of proposed model during training and training loss and validation loss at different poison stage of data poison on all the three attacks. We have the data set used here is skin data set. So finally, I'm going to conclude my presentation. This study delves into an impact of various data poisoning attacks on spiking neural networks, employing binary and multi-class data sets to enhance our insight. We developed a novel, lightweight yet effective spiking neural networks based model, SDSNN, and also proposed a novel metric to quantify the maximum potential effect of attacks on the model. The findings revealed that SDSNN with fewer parameters in comparison to spiking resin 18 and spiking VGG11 exhibit greater robustness against a considered attack. Notably, as data poisoning increased, a substantial decrease in accuracy was observed. Further research could explore impact of data poisoning on more intricate data sets and could uh, consider tasks beyond image classification. The development of even more robust model to withstand such attacks is also could also be explored. We can also implement many privacy preservation techniques. One such technique we can explore is differential privacy. Yeah. So these are the references that I've used in this presentation. Thank you.